All right, let's jump into another deep dive. This time, we're tackling something that might just bend your brain a little bit. The philosophy behind quantum chemistry. Yeah, you heard that right, philosophy and chemistry. Get ready, folks, because we're going where even the experts get a little lost
We
sometimes.
got that right. See, right at the heart of quantum mechanics, we've got this thing. It's called the wave function. Basically, it's a mathematical description. It tells us everything we could possibly know about a quantum system.
Yeah.
But there's a twist. This wave function, it exists in a space. Well, a space with potentially way more dimensions than the three that we experience every day.
Whoa, 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 hold on. More than three dimensions? I think that's where my brain starts to melt a little bit.
It's a brain melter for everyone, trust me.
Uh-huh.
Even Schrodinger, the guy who actually came up with the wave function, he struggled with this. Like at first he was trying to figure it out, make it fit into our regular three dimensions. But the more quantum mechanics developed, well, that just didn't work anymore.
So even the genius who came up with it couldn't quite grasp it completely. Okay, that makes me feel a little bit better about my own confusion.
You're in good company. And, all that confusion leads to a really interesting question. Like, what does this wave function thing actually represent? I mean, is it a real physical thing sitting out there in some higher dimension we can't see? Or is it just a math tool, something that helps us make predictions?
Okay, so that's where the philosophy part comes in.
Yeah.
So what are the different schools of thought on this? What are people saying?
So in one corner, you got the wave function realists. These guys, they believe the wave function is the real deal, like it's a real entity, and that higher dimensional space it lives in, it actually exists, even if we can't see it. It's kind of like, shadow puppet. The shadow is flat, 2D, but it's made by a 3D object. The wave function realist, they'd say our 3D world is like that shadow, a projection from a much bigger, higher dimensional reality, and that's described by the wave function.
Whoa, that's wild. So our reality is just a sliver of a much bigger picture.
That's the idea.
Yeah.
But not everyone's buying it. There's another group, they see the wave function as just a math tool. It's super useful for calculations and stuff, sure, but they don't think it's physically real. Think of it like a map, right? A map helps you navigate, helps you understand the terrain, but the map itself isn't the actual terrain.
Makes sense. One group sees it as the real territory, the other sees it as the map to the territory.
Exactly. But it gets even more interesting. There's this third view. It's kind of like the middle ground. They think maybe both sides are right in a way. They say maybe there's two spaces existing at the same time. One is that higher dimensional one for the wave function, and the other is our regular 3D one for the actual particles themselves. But how those two spaces interact, well, that's a whole other debate.
So we've got physicists arguing about extra dimensions and what's real, but where do chemists fit into all of this?
That's a great question. That takes us from this big theoretical stuff to the down and dirty world of molecules and reactions. And here's the thing. Even though the wave function and all its dimensions are at the core of quantum chemistry, chemists, they mostly work in our familiar 3D world. And they get a lot done that way.
So how do they make that jump from this abstract stuff to the practical stuff?
They use something called the orbital approximation. You might remember those pictures of atoms from high school, electrons going around the nucleus in paths. Well, those pictures, they're based on the orbital approximation. It simplifies things, imagines each electron kind of hanging out in its own orbital in 3D space.
Yeah, that rings a bell. But isn't that super simplified, especially since we've been talking about these higher dimensional wave functions and all?
You're absolutely right. It is a simplification, but a pretty smart one. It's a way for chemists to take that information from the multidimensional wave function and translate it into a form they can use in our 3D world.
Okay, so it's a simplification, but our source, this chemistry textbook by Atkins and DePaula, it has this quote that's kind of confusing. It says, "In the orbital approximation, we suppose that a reasonable first approximation to this exact wave function is obtained by thinking of each electron as occupying its own orbital." It's like it's contradicting itself.
It is a head scratcher, isn't it?
Okay.
But it points to something important. Even though it's called an approximation, the idea of electrons in their own orbitals, that's super central to how chemists understand molecules and how they behave.
So it's not just a quick fix. It's more like a core part of how they see chemistry.
Exactly, and it gets more interesting. Even when chemists factor in how electrons interact, something that the basic orbital approximation doesn't do, they still work with this idea, individual electrons in orbitals. It's fancier, sure, but the basic idea is still there.
It's like it's more than just a math trick then. It's actually shaping the way they view the whole world they study.
You got it. And that brings us to a really, really big question. Is this independent electron approximation something we can, eventually replace with a more accurate, a fully quantum mechanical description? Or is it something deeper? Maybe it's a clue to a whole different way of understanding reality, a separate chemical ontology.
Okay, now we're getting deep. A separate chemical ontology, that's a big idea. Tell me more about that.
Well, to get that, we
Yeah.
got to dig into how chemists actually do this translation. How they take the multidimensional wave function and bring it into our 3D world. They do it with a math process. It's called dimensional marginalization. It's like
Yeah.
this, imagine a tapestry, right? A beautiful, complex tapestry. It represents that full wave function. To make sense of it, you got to isolate a single thread. That's like a single electron. Then you use some fancy math and you kind of weave that thread into a separate but related 3D object. And that's the orbital.
That's a cool way to picture it. So they're basically pulling a piece of that higher dimensional information and making it tangible in our world.
Exactly. And that brings us back to those ontologies. If this independent electron approximation, with its focus on orbitals, if it's so good at explaining how molecules act, what does that tell us about reality itself? Is our 3D world more fundamental than some physicists think? Is chemistry, is it creating its own unique way of understanding reality, separate from physics?
Those are some heavy questions, and I don't think I have the answers right now. But I am definitely hooked. Tell me more about this chemical ontology. What else is there?
Well, there are a few different takes on how chemistry and physics, how they relate. Some people think we should try to make them fit together perfectly, find one big framework that covers everything. Others, they think some chemistry ideas like orbitals, well, they might not actually work with a truly quantum mechanical view. Like we should just ditch them altogether.
Whoa, that's pretty radical. Wouldn't that completely change how we teach and do chemistry?
Yeah. It'll be a huge change, yeah. And that brings us back to the third view, the one that our sources seem to like. It's called ontological independence. It says chemistry, even though it comes from physics, it's developed its own legitimate way of seeing reality.
So they're both looking at the same universe, but through totally different lenses, like using different tools, speaking different languages.
Exactly. And here's the fascinating part. This independent approach in chemistry, it's been crazy successful. That orbital approximation and other chemistry ideas, they've led to some huge breakthroughs in how we understand molecules and how they behave.
So these ideas about electrons and orbitals, they're actually helping us do real-world stuff, like
Okay.
making new medicines and materials.
Absolutely. And that shows just how powerful this chemical ontology is, even if it doesn't match perfectly with what physicists are saying.
So does that mean it's true in a way? Does the success of this independent electron approximation, does that tell us if orbitals really exist, even if, they're not exactly how physicists might describe them?
That is a seriously deep question. What does it even mean for a scientific idea to be real? Is it enough that it works? That it helps us explain and predict stuff? Or does it have to, match some deeper objective truth about the universe?
Man, those are some real head scratchers. It's amazing how diving into quantum chemistry leads to questions about reality and what we can even know.
It just shows you science isn't just about facts and figures. It's about how we ask questions, the models we build, the stories we tell about the world around us.
And it sounds like chemistry and physics might be telling slightly different stories, even though they're based on the same basic laws of the universe.
You hit the nail on the head there. And, exploring those different stories, it can be really mind-opening. It helps us see the world in new ways, appreciate how complex and nuanced science really is.
So instead of seeing these different ideas as a problem, we should be excited about them, like see them as a source of creativity and new ways of thinking.
Exactly. This back and forth between different scientific fields, between different ways of seeing the world, that's what drives progress. That's what leads to new discoveries.
So where do we go from here? Are chemistry and physics just gonna, live in their separate realities forever? Or is there a chance of finding one big unified theory, a way to explain everything?
It's tough to say for sure. It might be that the more we learn about both physics and chemistry, we'll find ways to bridge the gap between these different ways of describing things.
Maybe someday there'll be another Einstein, someone who just blows our minds with a new theory that connects the tiny world of atoms and quarks to the world of molecules and DNA, in ways we can't even imagine.
I wouldn't rule it out.
Yeah.
But even if that happens, I think we'll always need different scientific fields, each one focused on its own scale and level of complexity. The universe is huge and mysterious. We need lots of different points of view to understand it.
That's a beautiful thought. So we shouldn't be searching for one right answer. We should be celebrating all these different ways of doing science and all the richness that brings.
Couldn't have said it better myself.
Well, that's a really inspiring note to end on. I think we've reached the end of our deep dive for today, but the conversation, it doesn't have to stop here. We want you all to keep exploring these ideas, challenge your own assumptions, and never lose that sense of wonder about the universe.
And who knows, maybe one of you listening will be the one to discover that grand unified theory, that missing link between all the different ways we understand the world. So until next time, keep those brains working, keep asking those questions.
We'll see you on the next deep dive. And we're back, diving deeper into the surprisingly philosophical world of quantum chemistry. Before we took a little break, we were getting into this idea of a chemical ontology, basically. The idea that chemistry, even though it's based on physics, might have its own way of looking at reality.
And a big part of that is the independent electron approximation. It's not just a math trick. It's like baked into how chemists think and work.
We talked about how they use it to simplify like really complex calculations by thinking of electrons as if they're hanging out in these individual orbitals. But you said it's not really an approximation in the usual sense. What did you mean by that?
Well, most of the times when we talk about an approximation in science, we mean like a simplified model. It gets us kind of close to the right answer, but not all the way there. We know there's a more accurate solution out there, but it might be too hard or take too long to figure out.
So like when we use Newtonian physics to describe like everyday objects, even though we know Einstein's relativity is more accurate, more complete.
Exactly. It works for most things, most of the time. But this independent electron approximation, it's different. It's so deeply a part of chemistry. It's less like a temporary fix and more like a fundamental principle, like a starting point.
But if we're saying chemists have their own ontology, their own way of understanding things, doesn't that create a gap between them and physics? I mean, there has to be one truth about how the universe works, right?
That's a question that's been bugging scientists and philosophers forever. Like, how do these different fields of science with their own ways of doing things, how do they all fit together in the end? Our sources, they talk about three main positions on this.
All right, lay 'em on me. What are they?
The first one is called the reconciliation approach.
Yeah.
It basically says we got to find a way to make the ideas of chemistry and physics match up perfectly. Like find a common language so physicists and chemists can understand each other.
That sounds nice, but is it even possible?
People have tried, but it's tricky. The second idea is a lot more radical. It says that some chemistry ideas, like those orbitals we've been talking about, they might not work at all with a really deep quantum mechanical understanding. We should just get rid of them.
Whoa, that's a big change. Wouldn't that like turn chemistry upside down?
It'd be huge, yeah. And that brings us back to the third position, the one our sources seem to lean towards. It's called ontological independence. It says that chemistry, even though it builds on physics, it's created its own valid way of understanding reality.
So they're both looking at the same universe, but they're using different tools, different languages, like two different cultures.
Exactly. And here's the crazy thing. This way of doing chemistry, it's been incredibly successful. The orbital approximation and all these other chemistry ideas, they've helped us make huge leaps in understanding how molecules work.
So these abstract ideas about electrons and orbitals, they're actually helping us create new things like medicines and materials.
Absolutely. It shows just how powerful this chemical ontology is, even if it doesn't perfectly line up with what physicists say.
But does that mean it's true? Does the fact that the independent electron approximation works, does that tell us anything about whether orbitals really exist, even if they're not exactly what physicists might describe?
Now, that's a deep question. What does it even mean for a scientific idea to be real? Is it enough that it's useful? That it helps us explain things and make predictions? Or does it have to match some deeper objective truth about the universe?
Man, these are making my brain hurt. It's crazy how exploring quantum chemistry takes us to these questions about what's real and what we can know.
It just shows you science isn't just about facts and figures. It's about It's about how we frame our questions, the models we create, the stories we tell about the world.
And it sounds like chemistry and physics might be telling different stories, even though they're based on the same fundamental laws of nature.
You got it. And, exploring those different stories, it can be really enriching. It can help us see the world in totally new ways, appreciate how complex and nuanced science really is.
So instead of seeing these different ideas as a problem, we should be embracing them, see them as a source of creativity and new insights.
That's exactly right. This tension between different areas of science, between different ways of seeing things,
Yeah.
that's what drives progress. That's what leads to new discoveries.
So where do we go from here? Are chemistry and physics just gonna like stay in their separate worlds forever, or is there a chance we'll find some grand unified theory, some way to explain everything?
How It's hard to say for sure. It could be that as we learn more about both physics and chemistry, we'll find ways to connect these different viewpoints.
Maybe some future Einstein will come along and blow our minds with a new theory that connects the tiny world of atoms and quarks to the world of molecules and DNA, in ways we can't even imagine right now.
I wouldn't rule it out. But even if that happens, I think we'll always need different scientific fields, each one focusing on its own scale and level of complexity. The universe is huge and mysterious. We need lots of different perspectives to even begin to understand it.
That's a beautiful thought. So it's not about finding one right answer. It's about appreciating all these different approaches and recognizing that each one has value.
Couldn't have said it better myself.
Well, that's a really inspiring note. I think we've come to the end of our deep dive for today, but I want to hear from you. What's a question that's been on your mind as we've been exploring all of this?
That's a great question. As we've been talking about these different scientific ontologies, something I keep coming back to is the idea of emergence. How do we get new properties and behaviors from simpler parts interacting? We see it everywhere.
Hmm.
Atoms combining to form molecules, molecules forming cells, cells forming organisms. And each level of organization, it brings something new and unexpected.
It's like the whole is greater than the sum of its parts.
Exactly. And I wonder if this idea of emergence, could it help us bridge the gap between different areas of science? Maybe if we understand how complex systems come from simpler building blocks, we can start to see connections between seemingly unrelated fields like physics and chemistry. All right, we're back for the final stretch of our deep dive into, well, the weird and wonderful world of quantum chemistry. It's been quite a trip so far, wouldn't you say?
It really has. We've gone from those mind-bending wave functions and in who knows how many dimensions to the actual tools that chemists use to make sense of it all.
I gotta admit, before we started this, I never thought of chemistry as having its own, whole philosophy. I always thought it was just like physics put into practice using those fundamental laws.
Yeah, that's a pretty common idea. But as we've been exploring chemistry, it's not just about applying the rules of physics. It's about coming up with its own language, its own concepts, its own ways of understanding things. And a big part of that unique way of understanding is that independent electron approximation, right? The one we've been talking so much about. It's that idea that even though electrons are all tangled up with each other, influencing each other, chemists can simplify things by pretending they each live in their own little orbital.
It's a simplification, definitely, but it's been incredibly powerful. It's let chemists do amazing things, explaining how molecules behave, predicting things, and that's led to breakthroughs in all sorts of areas, like drug design, material science, you name it.
And what I find really cool is even though it's called an approximation, it's more than that, right? It's so fundamental to how chemists think. It suggests they're seeing reality differently, like what we called a separate chemical ontology.
Exactly. And it highlights something really important about science. It's not always about finding the absolute, most fundamental truth. Sometimes it's about finding the most useful way to describe and understand what we're looking at.
It's like using the right tool for the job. A carpenter, they wouldn't use a screwdriver to hammer in a nail. Even though both tools, they both work because of physics.
Perfect analogy. And for chemists, this whole independent electron approximation, with its focus on orbitals and individual electrons, it's been the right tool for so many things.
But does that mean, are we stuck with chemistry and physics having these totally different outlooks, these separate ontologies? Or is there a chance we'll find, a grand unified theory, one framework that brings everything together?
That's a question that's, well, it's kept people busy for centuries.
Yeah.
And I honestly don't know if we have the answer yet. Maybe as we get even better at physics and chemistry, we'll figure out how to connect those different points of view.
Maybe someday, there'll be another Einstein, someone who just blows our minds with a new theory that seamlessly connects the world of tiny particles to the world of molecules and DNA, something we can't even picture right now.
Hey, never say never. But even if that happens, I think we'll always need different scientific fields, each with its own way of talking, its own tools, its own ways of working. The universe is massive, it's complex. We need all those different views to even start to grasp it.
So it's not about finding the one right way to think about it. It's about recognizing that all these approaches, they all have something to offer.
Exactly. And that idea, embracing multiple perspectives, that's not just for science either. Something we can do in every part of life. When we're open to different ways of seeing things, we understand more, we see more possibilities.
That's a great point to take away. It reminds us the world is full of wonder, full of complexity, and the more ways we can look at it, the more we can appreciate how rich and beautiful it is.
This deep dive, it's been a journey into not just quantum chemistry, but like the nature of knowledge itself. We've seen how even the most basic ideas in science can be interpreted in different ways, how different fields develop their own ways of seeing reality, and how the search for knowledge, well, it never really ends.
And maybe the biggest thing we've learned is even though we might not have all the answers, that process of asking questions, of trying to understand, that's what makes life so interesting.
Couldn't have said it better myself. And on that note, I think we've reached the end of our deep dive. But the conversation, it doesn't have to end here. We hope you'll keep exploring these ideas, keep challenging what you think you know, and never stop being amazed by the universe.
And who knows, maybe one of you listening, you'll be the one to discover that grand unified theory, that bridge between all the different ways we make sense of the world. So keep those brains working, keep those questions coming.
We'll see you on the next deep dive.